Okay, great. Okay, so reminds me of last year. But here we go. So we're just going to do things like normal. I've asked Zoom to record the screen, so hopefully that'll work. Let's see. So a couple things that I learned last year. One is, of course, I'm not going to force anyone to turn their video on, but it does help me because I can kind of tell who's keeping up to what extent. Like I get a little feedback. Two, don't be shy to just burst in and ask questions. And something that seemed to work pretty well last year was students took advantage of the chat window. I have the chat window open as well, and I'm paying attention to it. But what I observed last year was like it's kind of easier to drop questions in there, and other students can ask while things keep going on. So please take advantage of that as well. Lastly, I haven't 100% checked because I was working on a lecture this morning, but the TA should post on Piazza Zoom links and how they're organizing today's session. So hopefully that gets propagated. Okay. Any questions before I begin? Well, maybe I should also mention that there was some comments, high-level comments in Piazza, and I'm very happy to talk about it. You know, for example, after class or something, I'll just be here on Zoom, and I can talk indefinitely. Okay. I'll also point out that some of those comments actually were brought up in our recent staff meeting, so we're at some level trying to address some of these things. Okay. All right. So I wanted to make one, before getting into the content of the lecture, I wanted to make one sort of high level and maybe over reductive comment, which is at some level, many of the problems we do together are solved sort of by two high level approaches. One is to try to identify the right kind of subproblem to decompose something, and at some level, some simple combination of brute force and saving your answers actually solves it. But really, this is why there's so much emphasis on that first step of the recursive spec, because that's when you identify the subproblem. If you do that right, things just melt away. The other sort of meta high-level algorithm that solves many problems is actually not to make a brand new algorithm from scratch, but think about how to change the input to some algorithms that we've already established in class or in lectures or in PSOs, okay? Where we've already proven a lot of nice properties that you can leverage. Okay. So that's sort of maybe two somewhat indirect perspectives that I think are sort of a different approach, but maybe it's good to consider these on some subproblems, and then failing those two, if you can't kind of figure out either a good, efficient kind of subproblem structure to decompose the original problem, or unable to maybe change the input and use something we've already proven, then maybe it's possible that there is a sort of creative way to change inputs, and actually the problem is quite general and could have solved that. All right, so marching on. So let me do a little bit of rewind. Okay, so we've been doing directed graphs for about a week now, starting last week with connectivity, whether point A can reach point B, okay, and which is solved by depth first search. But also, you know, we also studied these strongly connected components and this idea that you can decompose the graph into strongly connected components. That's sort of a very compact summary of who can reach who, made explicit in sort of that directed acyclic graph consisting of strongly connected components. Okay, so that's sort of, can point A get to point B at all? And then last time we started spending a little bit more attention on how how long it takes, and we asked this sort of simple question of trying to find the longest path in a graph. To my amazement, in this example, we had a path of length 10. But in general, it turns out in a general directed graph, this problem is quite hard. You can sort of take a SAT formula and make a gimmicky graph that reflects the SAT formula very well. But in a DAG, it's in fact linear time because DAGs are much easier to do this recursion plus caching strategy, this dynamic programming strategy, in particular because it's sort of no cycles in the graph tends to map to no cycles in the recursive dependencies. Okay, so finding the longest path in a directed acyclic graph, in fact, was about as easy as one could hope for. It took m plus n time. And as sort of a transition to today's lecture, we discussed at the end this problem of trying to find the shortest walk with at most some parameter k edges. Okay, so here I've labeled the edges in purple with some edge lengths, and you want to get from S to T using at most 8 edges or something, but minimizing the sum of those purple edge lengths. And you know, at some level, a priori, it wasn't clear if this was going to be hard or this was going to be easy. But it turns out that less than equal to k gives you an inductive structure where you can index these subproblems by the number of edges remaining. And then falling out of that is implicitly a directed acyclic graph, and you can solve this thing. All right, so today we'll talk about this problem of computing shortest walks. And here I set up an example that we can try to do interactively as best we can. So here's just an unweighted graph, so every edge is worth 1. If I forgot to label any edges, then that's just a bidirected edge. And we have 2 vertices and opposite endpoints labeled S and T. And so my question is, what is the shortest number of edges required to get from S to T? Maybe I'll wait 30 seconds to give you guys a chance to search, and then I'll do some kind of raise a hand to see who got what. So a couple suggestions of 7. Okay, let's see if this works. We can try this hand raising emoji. Maybe I'll ask, were people able to find a path of length at most 9? One person? Can't really tell. Okay. How many people were able to get a path of length 8 or less? Okay, say 2. How many people got a path of length 7 or less? It's like maybe 30%. Did anyone get a path of length 6? Jack, did you get a path of length 6? No, maybe not. Okay, so I guess everyone got 7, so as usual, I don't 100% know what the answer is. So maybe I'll just ask and listen to the chat which direction I should go. Should I go up or down first?
Up.
Up. Okay. Then I guess down or up?
Down.
Down. Okay, I guess I have 3 choices. I can go up or middle or, yeah.
The lower one.
Lower one?
Middle.
Okay. All right, here, what choices do we have? I can go this way, 1, 2, or 3 different ways. First, second, or third.
The second.
Second one to the right. Okay, here we can either go up or down or kind of to the left.
Up.
Up. Okay, here I can go up or down, I guess, or left.
Down.
Down. Okay, and then the last one is?
Right.
Right, okay. Good. Let me just check. 1, 2, 3, 4, 5, 6, 7. Okay, that is probably correct. Okay, so I think everyone has a good sense of what this problem is. My understanding from talking to the undergraduate TAs is that you guys might have done a little bit of shortest paths before as well. Okay. All right, so let me just define things a little bit formally. That was, of course, unweighted, but in general, we may have edge lengths. Okay. And, you know, I'm just basically looking at walks from S to T. And the length of the walk is the sum of lengths on those edges. Okay. And in particular, there's 2 maybe weird cases to be aware of. If I can't get from S to T, then we'll just say that's positive infinity. Okay, sort of like the worst distance. And it is possible that for any finite number, you can find a walk that's smaller. This occurs if you have a negative cycle. Okay. So in other words, the minimum length is not really bounded from below. In that case, we'll say it's negative infinity. And there's less and less properties. Maybe one I'll highlight is that even accounting for all those weird infinities, you do have a nice triangle inequality. Right? Here's the distance from S to U, the distance from U to T. And of course, altogether, this does give us a walk of some kind from S to T, so the upper bounds the distance from S to T. All right, so that is our goal for today. Just to take graphs and maybe 2 points and try to find the distance from one point to the next. And as we sometimes do, we'll work from sort of the simplest setting and gradually introduce more and more complexity and build up our ideas from bottom up. So as usual, I'll start with statics. Then we'll move on to unweighted graphs, like the example we just did. Then I'll look at strictly positive edge weights, okay, which sort of maps a little bit more to our physical intuition of distance. And I don't think we'll have time for this, so possibly next Tuesday, we'll discuss real weights, and in particular, some complexities that arise when you start having negative edges and worrying about negative cycles and things like this. All right, hopefully that'll be in person. So, all right, so we can look at first just finding shortest walks in a DAD. And as usual, when we have no cycles, that immediately tells us that the shortest walk is a path. Now I recognize that if you're already comfortable with some shortest path algorithms, you can apply those to DAG as well. But let us try to think from first principles. Given a DAG, and maybe I can give these edge lengths or something. How might we go about making an algorithm for a DAG?
Greedy, where you take the lowest weight one.
Okay, so greedy is always an idea. So let me then annotate to switch some edge labels. Okay, so what would be a good example? Let me just rig a counterexample to give you a hard time. Okay, so let me do something like this. Put a bunch of 3s here. I'll put kind of one big weight here so that you wouldn't want to use it. Okay. So possibly I'm misinterpreting greedy, but I'll still make a point. So one idea for a greedy approach is to always take the next minimum edge. So that would be 3, and you would probably find yourself following 3s all the way here. And what's going on in this example, of course, is that what you would like to do is use the 5 and eventually look past it and realize there's a bunch of zeros left, but a kind of very short-term greedy focus will never quite use that 5 edge before taking advantage only of 3s. So so I may have misinterpreted the greedy suggestion. Nonetheless, this greedy approach wouldn't be so hot. How about another? Yeah.
Could you maybe do a random path to T and then from there use the triangle inequality to say, to keep kind of finding a path that is less than or equal to the original paths?
Okay, so we could try to do. I guess that's a pretty interesting idea. So let me try to interpret this. We have this triangle inequality, and I'll suggest this is sort of like a very local kind of idea. And so a local search approach might try to find shortcuts based on this. So maybe like good question. Maybe you would identify that to get to this vertex, I can try to replace these two with those two. Maybe, yeah, it's not. I think one issue that makes kind of a purely local approach, and I'm only so triangle inequality only involves 3 vertices and stuff. So the general idea of only looking at a few vertices at a time is that suppose even in this example, which seems small, but suppose, in fact, these are sort of very, very long with many vertices. Maybe the total weight along that path is 3. Okay, so if I have many vertices, to sort of understand that I should be, well, I shouldn't have used red, but to understand that I should have taken the bottom path instead of the top, I would have to kind of exchange many vertices for many vertices. It's not an issue of just swapping out, very small shortcuts, 2 or 3 vertices at a time. That makes sense? And then enumerating over many vertices will become a little bit painful. Okay, so I think what I'd like to suggest is that the word DAG and not having cycles should almost reflexively inspire the idea of doing things recursively. Okay, sort of similar to what happened last lecture. So let me give a suggestion then, or trying to lay out a recursive approach. This is a lot like the longest walk example last time, but here I've defined, I want to invent something, an acronym for shortest walk. Okay, so maybe I'll say shortest walk of V will denote the length of the shortest walk from S to V. And now it's just a matter of filling out the recursion. I already wrote out 2 base cases. One if V is already S, then I don't have to go anywhere. And if V is not S, but maybe V is some vertex that has no incoming edges, then it just positive infinity. There's no way to get there. Now I left blank then sort of the interesting case. If I wanted to implement this recursion, I'm at some arbitrary vertex V. I want to kind of recursively calculate the shortest walk from S to V. What might I write at that bottom part? You're welcome to put it in the chat or say it out loud, whatever you're comfortable with.
For every outgoing edge, either take it or don't take it, and then calculate the weight with recursion and something.
Okay, so let me just start. Okay, so you're kind of looping over all the outgoing edges. And so here I'm kind of something, I guess, fill in this blank. Okay, outcoming, and then you said somehow recursively do something with that outgoing edge. So maybe SWW, I guess. So for V that'll be this edge and that edge and that edge. So these are the options for W. Okay, so all right, so I tried to sort of sketch out what was suggested, but maybe I missed something. Where do we go from here? What might, for example, be the squiggly, and so on and so forth?
Just determine the minimum weight.
Okay, we want the minimum. onto the shortest. So now we're minimizing over all outgoing edges the length of the walk to W, shortest walk to W. Minimum +1, okay? Because we do take one more edge, right? Here's a +1, +1. I guess if I had lengths, this might instead be, sorry. Jesus. If I had edge lengths, then maybe it would be like the length of the edge, UW plus the shortest walk. That would just be 1 if it was unweighted. Would it not be the length of the path? Yes, it would be a path. So I could have wrote paths or walks, so I could have wrote shortest path instead of shortest walk.
Shouldn't it be the incoming edge of V?
Oh, okay. So another idea is so instead of doing outgoing edges, maybe look at incoming edges, right? Because you kind of get from here to here, right? So okay, so maybe I will instead of doing outgoing edges, I'll do incoming edges. Okay, so this is already a little bit different than what we did last time. And I will try to get to that incoming vertex with as little distance as possible. So I'll recursively call that. And then I'll add the length of that edge into. Okay. So this is sort of just, this actually turns out to sort of reverse a little bit of the logic from the longest path problem. In particular, I'm kind of asking what comes before V on that shortest walk. So, because something has to come before V, since V is not S. We're just trying to guess it. And whatever is the right guess U, shortest walk U will inductively find the optimal way to get to U.
Should the incoming symbol be negative?
Should the incoming, well, good question. So should this be a negative sign? Is the question.
Oh no, I mean like the symbol of the incoming edge.
Yes. Thank you. Okay, so fine. So that would be a just a simple recursive algorithm that's really just saying whatever is the shortest walk to V, there's some vertex that comes before it, and recursively I can solve all the problems that come before. Now it's a DAX, there's a topological order, so there is a definite ordering to these problems. The problems will kind of, the dependencies will be the opposite direction from what we did for the longest path problem last class. But that key point that the DAG lets us do, oh, what is LW? Good point, that should be SW. I apologize. The key point remains that we can get away with this because it's a DAG. Kind of setting this up for a contrast when we remove this assumption next. All right, so now what is the running time? If we save the answers of our subproblems, this will be the same calculation we did last time. Ultimately, I'm summing over all the vertices. The time to solve the subproblem for that vertex. What is that running time? Okay, maybe I pay some constant time, to check these things or something like that. Plus, I'm looping over, it should be a V, I'm looping over the edges that go into V. So this is the in degree of V up to a constant. Okay. So if I'm solving this problem, I just need to check all the edges that come into it. And if I sum up, 1 for every vertex, of course I get n. And if I sum up the in degree over every vertex, I end up counting each edge once. It all adds up to a total number of edges. Okay. So even in weighted graphs, but if it's a DAG, we can do it as fast as we can hope to do just about anything. Okay. Any questions? Okay. All right, so where does that put us? Again, we've finished off DAGs. So now we're going to move on to unweighted graphs, which, what's the difference in looking at the in degrees compared to out degrees? Sure. So in degree, first definitionally, in degree is the number of edges going into a vertex. The out degree is the number of edges going out. Okay. And it just happened that last time we did longest path, the algorithm naturally looped over all the edges leaving a vertex. That's why out degree appeared. And then this time it was more natural to loop over the edges going into a vertex, which is why we get in degree. So last time we had a sum over out degrees. This time we have a sum over in degrees. But at the end of the day, either way counts each edge once. Because an edge can only go into one vertex and it can only go out of one vertex. So when it comes to tallying everything up, they both gave us n. Other questions? Okay. All right, so much for DAGs. So DAGs are always kind of a nice place to build some intuition. Particular, we can it's more easy to think about how to decompose problems recursively and kind of find a natural order of evaluation. So as we now move on to unweighted graphs, what's sort of happening, of course, you were all able to solve the unweighted example before, I think. We'll see. As we move on to unweighted graphs, sort of maybe a high-level idea to keep in mind is how do I take a graph that has cycles and be able to decompose it anyway, and at some level figure out how to deal with these cyclic dependencies and come to some definite conclusions anyway. That's maybe a little abstract, so let me begin. Okay, so here is that example from before, which, if I recall correctly, we thought that the solution was 7. We'll find out if that's true. Now, when we did things on DAGs, kind of implicit in that recursion was that we have the topological ordering of vertices, which actually tells us which vertex to evaluate first, right? In terms of which problems actually get solved and saved. It'll be the ones closest to the source at the beginning. Now, when we have cycles, we don't have a topological ordering, so we don't have an obvious order in which to do things. That's the only reason why this problem is not true. Now, we may not have a perfect kind of global ordering a priori, But we do know some obvious things. For example, I know that the only vertex at distance 0 is S. Right? I think that is not too controversial. And I know that the vertices that are at distance 1 is everyone that's one hop away from S. I feel quite good about the fact that a vertex is at distance 1 if and only if it has an edge from S. And having identified all the vertices at distance 1, it's a little bit easier to figure out who has distance 2. So just correct me if I make a mistake. This is very easy for me to make a mistake. But I believe those are all the vertices at distance 2. In particular, they're all the vertices that have an edge from somebody at distance 1, but weren't already at distance 1 or less. Okay. And now we start to see the pattern maybe. But the next question is, who's at distance 3? Distance 3 will be everyone who is one step away from distance 2, but not any closer. It's not a step away from distance 1. It's not a step away from distance 0. So I think that is 3. That is 3. Oh, right. That is 3. That is 3. That is 3. That is 3. Hopefully that's all the degree 3 vertices. We keep going. Degree 4 is going to be everyone one hop away from degree 3. It's more and more complicated. 4. That appears to be 4. That's also 4. I think that's all the distance 4 vertices. Please just blurt out something if I make a mistake. I made like a million mistakes preparing this morning. Having now figured out who is at distance 4 and 3 and 2 and 1 and 0, it becomes much easier to identify everyone at distance 5. Okay, so let me just be safe. I'm going to first circle them. S distance 5, that's distance 5, distance 5, 5. Distance 5. Having identified everyone at distance 5, here comes 6. This appears to be 6, 6, 6. I'm only confident because I had already figured out 5, 4, 3, 2, 1, 0. 7. Now we're close. There's T, like we wanted. This is also 7. So 7 is going to snake around. Oops. Okay. And then the last layer is 8. Like that. But really the key point going on here is now our induction argument is by distance, right? Because we have an unweighted graph, we can actually inductively identify by distance. Of course, you guys have all seen breadth first search before. Okay, so we get something like this. And so that's a breadth first search algorithm where we just incrementally label one layer at a time. Okay, we stop if we stop making progress. Okay. So this is probably not the implementation you guys have seen most often, but this is sort of really what's going on. I'll get to the Q stuff near the end. Okay. I'm just proceeding, distance 0, distance 1, distance 2, distance 3. And you just do some kind of simple bookkeeping where after determining layer 2, you go through the vertices of layer 2 and you find who you can reach at layer 3 that hasn't already been marked in layer 1. And if you do this all the way through, you end up only looking at each edge once. So just marking as you go along, it'll take linear time. Now, conceptually though, what I find kind of interesting is, what is the difference or similarities between our two algorithms? So in a DAG, recursion just works. Recursion plus caching. We got linear time algorithm. Breadth first search recursion wouldn't have just worked naively because you get these cyclic dependencies. But we did sort of figure out a different way to order the vertices. For this problem, it's very natural to order by distance. And because everything is integral, you can actually do a nice clean induction on the distances themselves. But consider this perspective. So here, hopefully I've done it correctly, but here again is all those layers of this graph. And imagine taking, some edges are useful for shortest paths. They go from layer 1 to layer 2, layer 2 to layer 3, layer 4 to layer 5. Others are not, right? They're going in the same layer, they're going backwards a layer. So what happens if I erase all of the useless edges, the ones that don't go forwards by a layer? So suppose I delete that. This is another place where it's easy to make a mistake. I delete that. Those two. Oh, I messed up on a. No, I didn't mess up. I delete that. That. I delete this. This. That. What else have I not done? Okay, I'm sure I missed one, but in any case. So now my question to you is, what is conspicuous about these remaining edges? Something has happened. It's a DAG. We've removed all cycles, and that makes sense, right? Because every edge is going forwards in distance, so it can never kind of go back in time. So sometimes these edges that are participate in shortest paths are called tight edges. And okay, so that's fine. And one thing that's nice is that among these tight edges, the distances give the topological ordering. That's not always true, but here it's true. And so now, sort of, what's kind of one way to interpret why breadth first search works, right? Because you're going by layer. When we did it together, we did layer 1, layer 2, layer 3. But that also meant we're following the topological ordering in this DAG of tight edges. So in fact, this was, to some extent, implicitly navigating and doing exactly the same thing as our DAG algorithm, but sort of implicitly. It's as if it had magically done the topological sort itself. But if you think about the order in which vertices are getting labeled and assigned their distances, it is in fact following the same order that problems would have been solved kind of bottom up in the DAG. Okay, so that's the kind of DAG interpretation. And of course, I'm sure you guys have been taught BFS in the other form, which is you insert things into a queue and you pull them out of a queue. Okay, and that works insofar as it's simulating exactly this process. Okay, good. That's all I had for unweighted graphs, which would bring us to the last segment of our presentation. But before starting positive weights, any questions about unweighted graphs or toggling between unweighted graphs and DAGs? Okay. All righty then. So let's finally do positively weighted general graphs. No negative weights, don't have to worry about negative cycles. All right, so this is a DAG, but ignore that. It's just a DAG because you just wanted to keep it uncluttered, I guess. Okay, so here's S and here's T. And I'll give you guys some time to stare at it. And then the question is, what is the length of the shortest path from S to T? And so I have some edge labels. I'll do some raise a hand after maybe 15 more seconds. Okay. Who found the path? Well, we'll use those emojis again. Who found the path of length at most 15? 7. Who found the path of at most 14? Still a few. Maybe they're all disappearing. We have 2, I think, definite 14s. 13? Anyone get 13 or less? Did anyone actually get 14, or was that just a hand that was rolled? Okay, so 15 was the bit. Okay. So I guess 15 was just the first one I saw. I didn't know it was going to be the best one. But here's one of 15 that I guess everyone saw. And apparently there's no better one. Okay, so this one wasn't so tough. Okay, fine. So again, I think we all understand roughly this problem then. Okay, so what's one way to think about it? And I'm going to present this in a way that sort of transitions from what we just talked about, unweighted graphs. Okay, so let me make an extra simple assumption just to develop some intuition, and let's just assume all the weights are integers. Okay, maybe if they're rational weights, you can clear denominators or something. But let's assume all the weights are integers. Okay, why? Because I can imagine taking this weighted graph with integer weights and splitting those edges however many times dictated by the weight. So I can think of an edge of weight 4 as 4 unweighted edges. I can think of an edge of weight 3 as 3 unweighted edges. Right? And so forth. So here's one where it's done nice and clean. And and to solve this problem, like this, we could always run breadth first search like last time while I build out the layers, right? This is now just an unweighted problem. So, we get layer 1, we get layer 2, we get layer 3, we get layer 4, layer 5, and so forth. So here it's all done, all those layers. There might be some mistakes possibly, but we could have split the edges and run breadth first search. Okay, that would be an algorithm. Of course, what is the obvious shortcoming of this approach? Yeah.
Can,
No, go ahead.
The size can grow exponentially.
Yeah, those edge weights can be big. They weren't particularly big in that example, but it could have been, way more than a number of nodes and stuff like that. Okay, so the only issue now is the running time when those edge lengths are very, very large. But what can we do to try to correct this? At the end of the day, I really only need to report the values of the vertices, the real vertices, not the fake ones that I've introduced. And so at some level, the only layers I'm really concerned with, layers 1 and 2 aren't so important, but layer 3 is important because there is a real vertex there. Layer 4 is also important. Layer 5 and layer 6, those also have real vertices. But again, layer 6 is not so important. Well, layer 6 wasn't this. It's so confusing. 7 isn't involved in anything. 9 is involved. 10, so forth, right? So I can imagine skipping the layers that don't have any real vertices in them. Okay. And I can try to reverse engineer what I would want to do to kind of make this work, right? What's really going on is that we still identify what is the first vertex or the second vertex closest to S. S would be the closest vertex. And here I would identify that this vertex circled in green is the next closest vertex, and so forth. So, if I do it this way, of course, we only have n real layers left, as opposed to exponentially many, because each one will actually have a real vertex in it. So, that is, why did I erase this? Okay, so that's sort of the approach we're going to take. which is to sort of skip all of those empty layers and only kind of figure out what's the next layer that actually contains a vertex. Okay, but the real point is we're still going to be increasing in distance. We're going to be increasing in distance, and we'll skip over the empty distances, which also may no longer be integer. In our example, they're integer, but maybe it's something weird. Maybe there's an edge of length pi. So our induction hypothesis will then actually be in order. They'll be on the vertices in order of distance away from S. So the base case is just S. The next case is the two closest vertices, S and the closest vertex. The next level will be the three closest vertices, which is S, the second closest vertex, and the third closest vertex, and so forth. If I've already figured out the 10 closest vertices to F, then I have enough information to figure out the 11th, to figure out the 12th, after that, and so forth. So this is, I first presented a version of the code where I'm not worrying too much about really fast writing times, just trying to set up the implicit induction hypothesis. So what's this algorithm doing? Here it's addressing the base case, where I just set distance S to be 0. And then here now comes sort of that induction step in a loop. So if I let given who I've labeled already, okay, so if I label, I mean I've already kind of figured out their distance. I'll figure out the next unlabeled vertex V. Okay, so V has not yet been assigned a distance. And I'll figure out sort of the distance from that labeled vertex plus that next edge. That'll identify the next closest vertex. Just loop. Gradually labeling one more vertex with each iteration. For integer weights, this is really doing breadth first search by skipping over the empty layers. So, let's take this unoptimized version and consider how long it would take. I'll open this up to the crowd. So how many iterations of the outer loop in step 2 would we have? At most. Okay, and then roughly how long would it take to do one of these inner loops? No data structures or anything, just looping over stuff. So from what I can tell, it seems like we basically just loop over each edge once. I go through each edge, UV. I check to see if U is labeled, and I add length of UV. I return the best sum I find. Okay. So M, as suggested. Okay, so sort of this initial version might take mn time. And as usual, we find ourselves asking, can we get a better running time? Okay, so, but the correctness is already established, and just having a polynomial running time is already established. Mn is, of course, much slower than breadth first search. We'll see how much we can push this down. Okay. So the thing we're going to leverage here, when we looped here over all these edges, is a little bit wasteful because at some level, each outer loop, I'm only giving one more distance assignment. So sort of the number of candidates only increases by a little bit. And there's a lot of edges I don't have to reevaluate. So to make this explicit, let's introduce, I'll call it tentative distance. This is sort of kind of the best distance I've found for an unlabeled vertex so far. So I haven't finalized this distance, but just based on who's already labeled. So I'm only worried about unlabeled vertices at some middle point of the algorithm. And I'll say the tentative distance of V is the minimum among U that are labeled, plus that rank. So I haven't committed to this distance yet. But each iteration, out of the unlabeled vertices, I'm choosing the one with the minimum tentative distance. Now, the point though is that each iteration, I label one more vertex V. So I label some vertex V with some distance like 10. And that might update the tentative distance, only for a few other vertices, right? Only in particular for the vertices that V can reach. Everyone else's tentative distance stays the same because no other distance labels have changed. So it's sort of wasteful to recompute everyone's distance label like we were doing in that loop. What would be better if we had a data structure that could kind of keep track of the vertices in order of their tentative distance and only update some of those tentative distances when necessary. Anyone want to suggest a data structure by name? Yeah, priority queues and heaps. Priority queues and heaps. I want to get the next smallest tentative distance vertex, and I want to be able to update them one at a time. Okay. So sometimes we think of heaps as just storing elements, or you can think of them as storing kind of key value pairs. Here I'll call a value a priority. So for us, a key will be a vertex that hasn't been labeled yet. The priority will be the tentative distance so far. I can insert keys. In this case, I'm allowed to decrease the key, decrease the priority of a key. So sometimes someone's tentative distance will go down. Okay. And then we want to keep removing the minimum tentative distance vertex. So priority queues or min heaps. And so I can use a priority queue as follows. So initially I'll set tentative of S to be 0 and everyone else will be positive infinity. So actually S hasn't been labeled yet. And I define, and I create some kind of priority queue. Think of like a binary heap first, and we'll talk about something a little bit fancier after that. And as long as that queue is not empty, I remove the vertex as the minimum tentative distance, just like we were doing. I make that the official distance for that vertex. And then for each of those edges that are leaving that labeled vertex, I check to see if I can improve the tentative distance. If I do, I'll decrease the priority accordingly. All right, so I'm just instrumenting and kind of shortcutting, removing some redundancy from the original algorithm. So suppose I'm using just regular binary heaps, so log n time per operation. So initiating this thing, I guess you guys can use this heapify operation with respect to ON, or even ON log n if you're doing it the lazy way, where you just insert everything. And removing the minimum vertex, this will take log n time. And to decrease a key in a binary heap also takes log n time. So now what's left is, I'll ask two questions. One is, how many iterations of this outer loop? Will we have? And one for every vertex. And okay, so this is a little tricky. How many, say on a per iteration for a fixed V, how many iterations do I have of that loop? Item C. For fixed V. Yes, the nth degree. We're just looping over the vertices. So if I combine everything together, I have n iterations of removing the min. So I'm paying n times log n. And then, summing all of these times log n will give me m log n. Okay. As usual, the nth degree sum to n. Okay. All right. So now we can actually do better by using a pretty remarkable data structure that we currently don't have the tools to fully analyze. Okay. So the bottleneck is this guy. Usually there's more edges than vertices. And log n is coming from the decreased priority. Okay, so the bottleneck is coming in the decreased priority. And in particular, if I can make that a constant, that would be great. That would improve my running time. Okay. So there is a data structure called a Fibonacci heap. By now, there's also other variants, okay? But this was the first time to get this bound. And it has a slightly different bound than we're used to. Okay, usually in data structures, we think about worst case bounds. Inserting takes up most log n time. Deleting takes up most log n time, so on and so forth. So this is not a worst case bound. This is what's called an amortized bound. That'll be a topic towards the end of the class. But as far as Fibonacci heaps go, here would be a precise statement. Suppose I called insert key I times, and I called decrease D, decrease key, or decrease D times, and I called remove min R times. In total, in the aggregate, the total amount of time I'll pay is I plus D plus R log n. Okay, what's the key point though? This is really saying that decrease takes constant time in a certain sense of on average, in the aggregate. The formal word is to say it takes constant amortized time. But for the sake of our discussion, we can just take this as a fact. And we'll discuss this amortized notion in greater detail later, much later. But now, if I take advantage of this amazing data structure, here I still pay log n time for every removed min, but now my decrease is taking on average constant time. So again, this was the out degree. This was n. So our running time will come out to n log n. And now I'm just summing a constant over the out degrees. So I get n. So this is m plus m log n, which improves m log n plus n log n from before. Okay, so it's pretty amazing data structure. This is by Tarjan, who was the hero of the strongly connected components, and I think it's Feldman. It might be Freeman. I think it's Feldman. Okay. And I think this was in the history of computer science, sort of a big victory for data structures. This was very kind of subtle and surprising that the difference maker was data structures. Okay, so this is also a remarkable running time because this is in a sense faster than sorting all the edges, so to speak. Right? It's really the running time of sorting all the vertices, so to speak, which you are sort of doing implicitly by being able to figure out their distances. Okay, so it's basically as best as we can do. Okay, so that is it. Why is the running time? Isn't the out degree? Okay, so what happened to this? Good question. So what happened to this mn factor? So I'm summing up the out degrees over all iterations of the outer loop. So if I sum up v, then I get m. And each v only appears once in the outer loop stage. I'm not sure if that was a good answer, Lenny. Isn't the out degree a nested? Yeah. So it's nested, but the sum of out degrees is m. And inside is just one decrease priority. Yeah, similar to what happened with DAGs and stuff like that. I could have made the same observation where if we drop all the edges that don't participate in shortest path, you have a DAG. You're implicitly doing something very similar to the DAG case. Other questions? Yes, it also has, I guess, assuming I copied it correctly, it also has amortized constant insertion time. Even if that was log n, though, it wouldn't be a bottleneck because it would only give us n log n.